Picture this, a bustling city intersection. Cars stream from all directions. It's a mesmerizing dance of motion and momentum. But unlike the cosmos, where celestial bodies follow predictable paths, traffic flow can be chaotic. This is where the power of mathematics comes in. It helps us bring order to the chaos, optimizing traffic flow for smoother, safer journeys. Think of intersections as cosmic crossroads. Each green light acts like a gravitational pull, guiding cars along their way. By understanding the mathematics of traffic flow, we can fine-tune these signals. We can make the dance of cars more efficient and less congested. Just like astronomers use telescopes to study distant galaxies, traffic engineers use data to understand traffic patterns. This data helps us unlock the secrets of traffic flow. By applying mathematical principles, we can transform congested intersections into well-choreographed ballets of motion. Welcome to the fascinating world of traffic flow optimization, where math and technology converge to keep our cities moving. Let's start by demystifying the science behind traffic flow. It's all about understanding how cars interact with each other and their environment. Imagine cars as molecules in a gas. When there are few cars, they move freely, like gas molecules at low density. However, as traffic density increases, cars start to influence each other's speed and spacing. This is similar to how gas molecules behave under pressure. This is where things get interesting. Traffic flow isn't just about the number of cars, it's also about speed, density, and the distance between vehicles. These factors are interconnected, forming a complex system that can be analyzed and optimized using mathematical models. By understanding these relationships, we can predict how changing one factor, such as green light duration, will impact overall traffic flow. It's like solving a cosmic puzzle, piecing together data and equations to unlock smoother, more efficient traffic patterns. Before we delve into the mathematical formulas, we need data. Just as astronomers observe stars to understand the universe, traffic engineers observe cars to understand traffic patterns. This data collection is the foundation of traffic flow optimization. One of the most common methods is traffic counting. This involves using sensors or cameras to record the number of vehicles passing a specific point during a given time interval. It's like counting stars in a specific region of the night sky. But we don't just count cars. We also track their speed, direction, and the time of day. This data, collected over time, reveals patterns and trends that are crucial for optimizing traffic flow. Think of it as creating a cosmic map of traffic movement. The more data we gather, the more detailed and accurate our map becomes. This allows us to identify congestion hotspots, predict traffic volumes, and fine-tune traffic signals for optimal performance. We all know that traffic volumes fluctuate throughout the day. The morning and evening rush hours are prime examples of predictable peaks in traffic density. But how can we use this knowledge to optimize traffic flow? The answer lies in the realm of probability. Probability helps us predict the likelihood of events, such as the chances of heavy traffic during specific hours. By analyzing historical traffic data, we can identify patterns and use them to forecast future traffic conditions. For instance, if data shows that a particular intersection experiences heavy traffic between 5 p.m. and 6 p.m. on weekdays, we can adjust traffic signal timing to accommodate the increased volume. It's like predicting the movement of celestial bodies based on their past trajectories. By incorporating probability into our traffic models, we can proactively manage traffic flow, minimize congestion, and reduce waiting times. It's about using the power of prediction to create a smoother, more efficient traffic experience. Section 5, the green light, tango time and motion. Now, let's dive into the heart of traffic flow optimization, the green light. The duration of a green light is a critical factor in determining how many cars can pass through an intersection during a given cycle. It's a delicate balancing act. A longer green light may seem like the solution to moving more cars. However, it can also lead to longer waiting times for vehicles on other approaches, potentially causing congestion elsewhere. Think of it as a cosmic dance between time and motion. The green light sets the rhythm, dictating the flow of vehicles. To determine the optimal green light duration, we need to consider several factors: the number of lanes, the speed limit, and, most importantly, the volume of traffic approaching from each direction. This is where mathematical equations come into play, allowing us to calculate the ideal green light time for each traffic movement. Section 6. The equation of flow green means go. One of the fundamental equations in traffic signal timing is the calculation of the total cycle length. This represents the time it takes for all approaches to an intersection to receive a green light. The total cycle length is typically divided into intervals for green, yellow, and all red clearance times. The formula for calculating the total cycle length, C, is C equals lost time divided by 1 minus the critical flow ratio. Don't let the equation intimidate you. Let's break it down. Lost time refers to the time during a signal cycle when vehicles are not moving due to factors like vehicle startup time and pedestrian crossings. It's the time lost between green lights. Critical flow ratio is the ratio of the actual traffic flow rate to the saturation flow rate. The saturation flow rate represents the maximum number of vehicles that can pass through an intersection per lane per hour under ideal conditions. By plugging in the values for lost time and critical flow ratio, we can calculate the optimal total cycle length for an intersection. Section 7. Yellow Light Symphony. A moment of transition. Between the green light's invitation to move and the red light's command to halt, there exists a brief but crucial interlude, the yellow light. This amber signal serves as a warning, a cosmic pause that allows vehicles already in the intersection to clear safely before the light changes to red. The duration of the yellow light is critical for safety. If it's too short, drivers may be caught in the dilemma of slamming on their brakes or rushing through the intersection, increasing the risk of accidents. Conversely, an excessively long yellow light can lead to unnecessary delays and driver frustration. The ideal yellow light duration is typically determined based on factors like the speed limit and the perception reaction time of drivers. This involves considering the time it takes for a driver to perceive the yellow light and react by braking or accelerating. The yellow light, though fleeting, plays a vital role in maintaining a smooth and safe traffic flow. Section 8. Traffic Density Choreography, Balancing the Flow. Now that we understand how to calculate the total cycle length, let's explore how to allocate green time to each traffic movement. The goal is to optimize traffic flow by giving more green time to approaches with higher traffic volumes. This is where the concept of proportional allocation comes into play. Imagine a cosmic scale with traffic volume on one side and green light duration on the other. Proportional allocation ensures that the green light time is distributed in proportion to the traffic demand from each direction. For example, if one approach to an intersection carries twice as much traffic as another approach, it should receive twice as much green time. This ensures that the green light time is used efficiently, minimizing delays and maximizing throughput at the intersection. Section 9. Real-time adjustments conducting the traffic orchestra. While pre-timed signal settings based on historical data provide a good starting point, traffic patterns can be unpredictable. Unexpected events like accidents, construction, or special events can significantly impact traffic flow. This is where the power of real-time adjustments comes into play. Intelligent Transportation Systems, or ITS, use sensors, cameras, and communication technologies to monitor traffic conditions in real time. These systems can detect changes in traffic patterns and dynamically adjust signal timings to optimize flow and minimize congestion. For instance, if a sensor detects a sudden increase in traffic volume on a particular approach, the system can extend the green light duration for that approach, allowing more vehicles to clear the intersection. It's like having a conductor fine-tuning the orchestra's tempo in response to the music's dynamics. Section 10. A data-driven future navigating the cosmic traffic jam. As our cities grow and traffic volumes continue to rise, optimizing traffic flow is no longer a luxury, but a necessity. By harnessing the power of mathematics, data analysis, and technology, We can transform our transportation systems and create smarter, more efficient cities. This data-driven approach to traffic management offers numerous benefits. It reduces travel times, improves fuel efficiency and lowers greenhouse gas emissions. Moreover, it enhances safety by minimizing congestion and reducing the risk of accidents. Just as astronomers continue to explore the vastness of the cosmos, traffic engineers are constantly seeking new and innovative ways to optimize traffic flow. The journey towards a future of seamless and efficient transportation is ongoing, guided by the principles of mathematics, technology, and a deep understanding of the cosmic dance of cars.